Howdy doody, boys and girls. This PowerPoint will be done in two sets. There'll be the first 12 slides, which will focus on the skeletal system, and then there'll be the last 8 slides, which will focus on the muscular system. Not doing too much detail, but just enough so that you can appreciate each of the two systems, a little bit about how they work together. But the foci of each section will be also bone health, nutrition for bone health, and nutrition for muscle health, which is the topic of Wednesday and Thursday. Okay. So what you're looking at right here, we're starting with the organization of life. Just to remind us that while we are typically interested in organs and nutritional health for our heart, health for our, good health for our kidneys, too much protein when you're dosing high on protein all the time because you're building muscle or working out, people have to watch out for is doing damage to their liver, because their liver makes all those proteins and has to detoxify a lot of stuff, and kidneys having to filter all that from the blood. So there's a health aspect to that. While we're interested in organ health and our body feeling good, those organs, we have to recall, are themselves made up of tissues. That is a whole bunch of cells, thousands of cells, all look the same, functioning the same towards one goal, towards one end. So this is group work right here. Here we see heart tissue. But each of those right there that I'm looking at in the heart tissue are made of cells. So tissues are made of individual cells. And so when you feel sick or when you don't feel good, it's because your cells are sick. And collectively, when enough of your cells are not feeling good, that's when you begin to feel the pain or discomfort. Okay, so we want to keep those cells healthy. So how do we keep cells healthy? Well, the molecules that are inside of them, that are around them, need to be the right kind of molecules and in the right amounts. Okay, and those molecules are then made of atoms. And so it's important to get good nutrition, because nutrition gives us the molecules and the atoms we need to help our cells do their job together as a tissue. If there's one weak link, that's going to be one weak part of the heart in this case. And that heart then, which circulates blood to the entire body as a cardio respiratory system, becomes affected, all because of something happening at the cellular level. So it's real important we keep that in mind. So when we look at bone, we're going to look at the general skeleton and some broad things in the skeletal system, but you'll be also watching the video and doing some reading that are in particular about nutrition and how bone is formed. Once you understand how bone or muscle is formed and what happens at the cellular level, you'll appreciate why good nutrition is important for them. And just to remind you of what all is involved in cell functioning, here are some of the organelles. Organelles is like saying little organs. These are all the tiny organs of individual cells. Each one of those alive and of itself, not the organelles, but each one of those cells are alive and of itself because of these organs. So you can go down this list here, and while not all cells have this generic shape, they do have all these components. A membranous system to transport molecules and proteins, a mitochondrion to produce energy for those cells by ATP, chromosome for digestion, has full of enzymes which break down materials that are brought in. So all kinds of things going on here, processing, sending messages in and out of the cells, as we'll see here shortly. So let's just go ahead and get into the skeletal system, the musculoskeletal system, as it's often referred to, because the two work in tandem. So the skeleton is an anchor for muscles. Muscles flex and muscles move, but unless they're attached to something, like I've mentioned before, nothing gets done. So muscles attached to bone through tendons. And there are about 206 bones in the human adult that are in some way, form, or fashion attached to a muscle in order to allow movement. There's only one bone in the body. Bonus, if you can figure it out, I guess you can Google it, that is not attached to any muscle or any other bone. So there are two parts of the skeleton, the axial and the appendicular. The axial is all the center, the axis. That's going to be your spine up to your skull. Everything else that comes off of it, the ribs, the shoulder blades, scapula, the hip, all that is appendicular. Okay, with that, you're going to have a lot of irregularly shaped bones here, a lot of flat bone here in the axial skeleton, and then in the appendicular, excuse me, you'll have mostly long bones. All right, so what do you think is a better model of a bone? Chalk or sponge? Well, I do give you kind of an answer here, but in reality, both. It just depends on what part of the bone you're talking about. When we think of bone, we often think of the bone in a chicken, right? Because we get to the chicken bone, we see it looks like a lifeless white or brown structure, hard, brittle structure. Whenever you come across bones in nature, whether of a cow, a deer, a dog, on the side of the road or somewhere, or a cat, these bones, they usually look lifeless. They're whitish and they're hard, and so they look lifeless. But in all reality, bone is very much alive. It's alive tissue. So here you see this compact bone. The thin border is more like the chalk, but it is correct. Most of it is more like a sponge. A lot of holes, a lot of ins and outs. So here's a cross section of a long bone, and you may or may not have known this. I think it's pretty cool, but blood is made by bone. Well, maybe not by bone, but it's made inside the bone. So you have blood stem cells harbored right here in what we call the epiphysis of long bones. You don't have to know that. We'll just call it the head of long bones. So this is primarily in your hips, top of your shoulders. As you're young, once you get past puberty, a little less and less bone is formed there. It does stay in your hips bones though. So what is in all these holes? You can see is tiny capillaries. So there's a lot of circulation of blood through your bone. There's a lot of bleeding when a bone breaks because it's filled with vessels, tiny vessels that are running throughout the bone. All right, and those vessels get ripped and torn whenever a bone breaks, and that's why there's a lot of fluid and swelling and buildup. There's also a lot of nerve tissue, and in the center there's kind of a hollow point where the marrow is. This is what, if you've ever fed bones to dogs, or in this case, I have some land and property you go out on, and you will find a deer skeleton, or I've even found a cattle skeleton, and I always just leave it there. It's so interesting to see where those pieces over time end up. And that's because every night critters come and they gnaw and they chew, and even whatever critters don't gnaw and chew, you have bacteria and fungi that get in, and they will continue to eat on those bones because they can sense that fatty tissue of the yellow marrow inside the bones. And anyone who's made bone soup or leave the bones for flavor, that will leach out into the water, and you'll get that flavor, that added flavor to the food because of the marrow in the bone. So you want to remember this picture. This is a cross section of the bone. There's compact bone and there's spongy bone. Okay, it's a spongy bone. And then there's the marrow, which is kind of a hollow tube filled with yellow marrow and red marrow, which we'll talk about. Well, red marrow is up here, which we'll talk about in coming slides. So you may need to come back to this picture off and on. So what passes through the tubes and spaces inside, as we just said, blood vessels and nerves. Periosteum is what we call that very tough, thin layer. You might have gotten to this eating at the end of a chicken leg or something. It's just a paper thin, or thinner than paper layer, but a very tough layer. Haversian canals, it's a network of tubes that contain blood vessels and nerves. Those are all inside here. So right here, this is what we'd call the Haversian canal. So bone marrow are cavities. A cavity is an open space that contains soft tissue. It's not hardened. It's surrounded by that compact bone. Remember, that's hard, so it's protective on the outside. But there are two types of bone marrow within the bone, the yellow and the red marrow. Yellow is made up of fat cells, again, the flavor we were just referring to. And then red marrow produces the red blood cells, some of the white blood cells and fragments called platelets for clotting that enter circulation. So all that blood that's in your circulation originated from the bone, the head of long bones primarily, and some flat bones. Cartilage, now this comes, these are for protection. Cartilage is for protection. It's at the tips and the ends of all joint bones. Any bone, any point in your body where you have an articulation, an ability to move or twist, there's going to be cartilage there. And some of you who've played sports probably know this because maybe you've worn out your cartilage or your knees, and you've gone to the doctor for this. So these cartilage cells are scattered in a network of protein fibers. So you can see already, not only do your cells of your bones also need energy, but they need protein. Two proteins are elastin and collagen. Elastin and collagen. Collagen for toughness, elastin for flexibility. There is an amount of flexibility in the bone. If they were too hard, filled with just collagen, then it would be very brittle. So you need both those proteins. Cartilage does not contain blood vessels. This is why it takes so long for the cartilage to heal, basically by diffusion from the synovial fluid, which we'll see in a future slide here. The synovial fluid that surrounds the joints, bathe the joints in nutrition, and that moves very slowly. So cartilage is dense and fibrous with protein and fibers and cells just scattered around. Supports a lot of weight despite its extreme flexibility, but it needs to have that sway. So how does bone form? Well, it actually, during development in the womb, as you may know, babies have very soft bones. They can bend before they break. And that's because they're filled with a lot of cartilage. Over time, that cartilage is replaced by bone tissue. So it's not that one is coming in and taking over. It's that the cartilage is actually ossifying. The cartilage itself is being converted into bone. You could say cartilage is a precursor to bone as it becomes ossified, and that takes minerals, mineralization and calcification. All right, so you'll see a little bit of that during the video and modeling and remodeling. So the three types of cells we're interested in are osteoblasts. These osteoblast, bone forming, create bone, new bone material. Osteocytes, cytes means cells, bone cells, maintain the cellular activities of the bone. So these are the ones, any bone tissue that you see are typically going to be osteocytes. This is what forms the bones. Make up the bones, excuse me. When I say forms, we want to say osteoblasts. That's what create or forms a bone. But once the bone is created, that material, the cells of the bone, are called osteocytes. Then there are these other kinds of cells called osteoclasts that break down bone. Why would we have cells that break down bone? Good question, right? You want to look that up. But I can tell you this, if you ever had to repair bone, you're going to have to break down old bone tissue before you can rebuild new. Osteoclasts definitely take a role in that. All right. Osteoclasts are for breaking down. Osteoblasts are for creating a bone. Osteoclasts are more prevalent in the early years of growth and development, from being an embryo to the age of about 7, and then less and less as time goes on. But if you're malnourished or undernourished, not enough calcium, there's a lot of systems in your body that need calcium. Your nervous system needs calcium. Your muscular system to move, you need calcium. Blood clotting requires calcium. There are some really vital activities that require calcium. Guess what? If you're malnourished or undernourished in calcium, the first place that it's going to come from is say, hey, we need some reserves. It's going to go to the bone. And those osteoclasts will be activated to break down bone. Why? Because when you break down bone, what you're going to release is calcium. So the calcium comes then from the bone, enters the bloodstream, and the blood, the nervous system, the heart, all those things will get their load of calcium. Bones will be the last thing that you'll need. So bones will be the first place, your skin and your hair will be the first place you see the effects of a deficiency of calcium, because your body's pulling it from those places in order to put it in the more vital aspects of your physiology, your body. And that's what osteoclasts do. They'll break down bone when necessary for reformation or even to release calcium to the bloodstream. All right, so bone formation occurs in babies and children, as we were just mentioning. 7 months before birth, cartilage is gradually replaced by bone. When a person grows, the growth plates are lengthening in the long bones by converting cartilage to bone. When you stop growing, those growth plates are then filled with bone. All right, it ossifies is the word, and we do that with minerals. Adults do retain some cartilage, tips of the nose, ears, where ribs attach, and the sternum. These things continue to grow very slowly throughout your lifetime, which is why old men usually have big ears and big noses, or long noses and droopy ears. All right, so depending on the type of movement, a joint is classified as immovable, not able to move, slightly movable, get some movement in it like your wrist, or freely movable. So immovable joints would be like in your skull. Slightly movable joints are like between the lower leg, the joints between the adjacent vertebrae, your spine. Freely movable are all these other types of joints we're about to look at. So everywhere you have a joint or an articulation, okay, shoulders where you move at 360 degrees, your elbow and your knees, which are hinge joints, which move 90, only on that one plane, 90-degree angle. All these are weak spots where injuries can occur. And so you have a lot of minor muscle that surrounds those joints. It's wrapped in cartilaginous tissue, in bursal sacs, in lubricating areas, with a lot of muscle trying to stabilize that joint so that the joint only moves in the area. Now, if you play a lot of sports or high impact sports, obviously, you're going to have a lot of wear and tear, and you have the potential of tearing some of those tendons and ligaments and even ripping a muscle. And if you do none of those things, for sure, even if you played high school sports, by 25, and give or take, you're going to start feeling the effects of that. And by 35, you might have even had your first procedure done. And as you get older, those joint issues are going to bother you only more and more. It just comes with the territory of wear and tear. So I'm going to finish with this slide here. Tendons attach muscles to bones. Okay, so what anchors the muscles? Tendons do to the bones. When muscles contract, tendons pull on the bones to cause that movement. Ligaments connect bone to bone. Okay, so ACL, anterior cruciate ligament, is a common ligament between the lower leg and the upper leg that a lot of athletes tear, or even just regular people will tear those ligaments. So think of the L, ACL. L stands for ligament. It holds the two bones together. A bone moves when it shouldn't. Otherwise, muscles to bone means tendons. The synovial fluid I referenced just moments ago lubricates the ends of bones so they can slide past each other and move more smoothly. Okay, synovial fluid is secreted by a membranous sac. It is also, we get stiff and we stay still for long periods of time. Some gases build up. We don't circulate that synovial fluid because we're not bending those joints much in little gas pockets. So when you do move, when you stand up, when you first wake up in the morning, you hear those popping of your knuckles, you're releasing those little air pockets, like knuckle farts. Knuckle farts. Nah, it's just releasing that gas. You're popping it, and you're pushing it, and you're forcing it. So it's good to kind of move all your joints to some degree and stretch them. Keep that synovial fluid circulating, because if not, the cartilage is not. Especially, there's times you get an injury where you want to remain immobile, but a lot of times when it's not a break or something so severe, you want to begin to slowly move it as much as possible, because you're going to keep that synovial fluid circulating within those little, and here's where it would be. Let me just go ahead and show you. So these are all synovial joints. So there's sacs around this. It's fluid, mostly water, but also proteins and enzymes that will help to heal faster. And just speaking in reference to injuries here. Okay, that's my time. 20 minutes, and hope you enjoyed. Hope this was helpful. Taken together, we should have a general understanding of bone, the skeleton, as an introduction.